In mathematics, the continuum hypothesis is a hypothesis about the possible sizes of infinite sets. It states, there is no set whose cardinality is strictly between that of the integers and the real numbers. The continuum hypothesis was advanced by Georg Cantor in 1878, and establishing its truth or falsehood is the first of Hilbert's 23 problems presented in 1900. The answer to this problem is independent of ZFC set theory, so that either the continuum hypothesis or its negation can be added as an axiom to ZFC set theory, with the resulting theory being consistent if and only if ZFC is consistent. This independence was proved in 1963 by Paul Cohen, complementing earlier work by Kurt Gödel in 1940. The name of the hypothesis comes from the term the continuum for the real numbers. It is abbreviated CH, cardinality of infinite sets. Two sets are said to have the same cardinality or cardinal number if there exists a bijection between them. Intuitively, for two sets S and T to have the same cardinality means that it is possible to pair off elements of S with elements of T in such a fashion that every element of S is paired off with exactly one element of T and vice versa. Hence, the set banana, apple, pear has the same cardinality as yellow, red, green. With infinite sets such as the set of integers or rational numbers, this becomes more complicated to demonstrate. The rational numbers seemingly form a counterexample to the continuum hypothesis. The integers form a proper subset of the rationals, which themselves form a proper subset of the reals, so intuitively, there are more rational numbers than integers, and more real numbers than rational numbers. However, this intuitive analysis does not take account of the fact that all three sets are infinite. It turns out the rational numbers can actually be placed in one-to-one correspondence with the integers, and therefore the set of rational numbers is the same size as the set of integers. They are both countable sets. Cantor gave two proofs that the cardinality of the set of integers is strictly smaller than that of the set of real numbers. His proofs, however, give no indication of the extent to which the cardinality of the integers is less than that of the real numbers. Cantor proposed the continuum hypothesis as a possible solution to this question. The hypothesis states that the set of real numbers has minimal possible cardinality which is greater than the cardinality of the set of integers. Equivalently, as the cardinality of the integers is and the cardinality of the real numbers is. The continuum hypothesis says that there is no set for which, assuming the axiom of choice, there is a smallest cardinal number greater than, and the continuum hypothesis is in turn equivalent to the equality. A consequence of the continuum hypothesis is that every infinite subset of the real numbers either has the same cardinality as the integers or the same cardinality as the entire set of the reals. There is also a generalization of the continuum hypothesis called the generalized continuum hypothesis, which says that for all ordinals, that is, GCH asserts that the cardinality of the power set of any infinite set is the smallest cardinality greater than that of the set. Independence from ZFC. Cantor believed the continuum hypothesis to be true and tried for many years to prove it, in vain. It became the first on David Hilbert's list of important open questions that was presented at the International Congress of Mathematicians in the year 1900 in Paris. Axiomatic set theory was at that point not yet formulated. Kurt Gödel showed in 1940 that the continuum hypothesis cannot be disproved from the standard Zermelo-Fraenkel set theory, even if the axiom of choice is adopted. Paul Cohen showed in 1963 that CH cannot be proven from those same axioms either in Cohen. Hence, CH is independent of ZFC. Both of these results assume that the Zermelo-Fraenkel axioms are consistent. This assumption is widely believed to be true. Cohen was awarded the Fields Medal in 1966 for his proof. The continuum hypothesis is closely related to many statements in analysis, point set topology and measure theory. As a result of its independence, many substantial conjectures in those fields have subsequently been shown to be independent as well. So far, CH appears to be independent of all known large cardinal axioms in the context of ZFC. The independence from ZFC means that prove or disproving the CH within ZFC is impossible. However, Gödel and Cohen's negative results are not universally accepted as disposing of the hypothesis. Hilbert's problem remains an active topic of research. See Woodin and Kollner for an overview of the current research status. The continuum hypothesis was not the first statement shown to be independent of ZFC. An immediate consequence of Gödel's incompleteness theorem, which was published in 1931, is that there is a formal statement expressing the consistency of ZFC that is independent of ZFC, assuming that ZFC is consistent. The continuum hypothesis and the axiom of choice were among the first mathematical statements shown to be independent of ZF set theory. These proofs of independence were not completed until Paul Cohen developed forcing in the 1960s. They all rely on the assumption that ZF is consistent. These proofs are called proofs of relative consistency. A result of Solovay, proved shortly after Cohen's result on the independence of the continuum hypothesis, shows that in any model of ZFC, if is a cardinal of uncountable cofinality, then there is a forcing extension in which, however, it is not consistent to assume is or any cardinal with cofinality. Arguments for and against CH. Gödel believed that CH is false and that his proof that CH is consistent with ZFC only shows that the Zermelo-Fraenkel axioms do not adequately characterize the universe of sets. Gödel was a Platonist and therefore had no problems with asserting the truth and falsehood of statements independent of their provability. Cohen, though a formalist, also tended towards rejecting CH. Historically, mathematicians who favored a rich and large universe of sets were against CH, while those favoring neat and controllable universe favored CH. Parallel arguments were made for and against the axiom of constructibility, which implies CH. More recently, Matthew Foreman has pointed out that ontological maximalism can actually be used to argue in favor of CH. Because among models that have the same rails, models with more sets of rails have a better chance of satisfying CH. Another viewpoint is that the conception of set is not specific enough to determine whether CH is true or false. This viewpoint was advanced as early as 1923 by Skolem, even before Gödel's first incompleteness theorem. Skolem argued on the basis of what is now known as Skolem's paradox, and it was later supported by the independence of CH from the axioms of ZFC. Since these axioms are enough to establish the elementary properties of sets and cardinalities, in order to argue against this viewpoint, it would be sufficient to demonstrate new axioms that are supported by intuition and resolve CH in one direction or another. Although the axiom of constructibility does resolve CH, it is not generally considered to be intuitively true any more than CH is generally considered to be false. At least two other axioms have been proposed that have implications for the continuum hypothesis. Although these axioms have not currently found wide acceptance in the mathematical community. In 1986, Chris Freiling presented an argument against CH by showing that the negation of CH is equivalent to Freiling's axiom of symmetry, a statement about probabilities. Freiling believes this axiom is intuitively true, but others have disagreed. A difficult argument against CH developed by W. Hugh Woodin has attracted considerable attention since the year 2000. Foreman does not reject Woodin's argument outright but urges caution. Solomon Pfefferman has made a complex philosophical argument that CH is not a definite mathematical problem. He proposes a theory of definiteness using a semi-intuitionistic subsystem of ZF that accepts classical logic for bounded quantifiers but uses intuitionistic logic for unbounded ones, and suggests that a proposition is mathematically definite if the semi-intuitionistic theory can prove. He conjectures that CH is not definite according to this notion, and proposes that CH should therefore be considered not to have a truth value. Peter Kolner wrote a critical commentary on Pfefferman's article. Joel David Hampkins proposes a multiverse approach to set theory and argues that the continuum hypothesis is settled on the multiverse view by our extensive knowledge about how it behaves in the multiverse, and as a result it can no longer be settled in the manner formerly hoped for. In a related vein, Saharan Scheller wrote that he does not agree with the pure Platonic view that the interesting problems in set theory can be decided, that we just have to discover the additional axiom. My mental picture is that we have many possible set theories, all conforming to ZFC, the generalized continuum hypothesis. The generalized continuum hypothesis states that if an infinite set's cardinality lies between that of an infinite set S and that of the power set of S, then it either has the same cardinality as the set S or the same cardinality as the power set of S. That is, for any infinite cardinal there is no cardinal such that GCH is equivalent to. For every ordinal, the Bethe numbers provide an alternate notation for this condition. It was first suggested by Jourdain. Like CH, GCH is also independent of ZFC, but Sierpinski proved that ZF plus GCH implies the axiom of choice. So choice and GCH are not independent in ZF. There are no models of ZF in which GCH holds and AC fails. To prove this, Sierpinski showed GCH implies that every cardinality n is smaller than some Aleph number, and thus can be ordered. This is done by showing that n is smaller than which is smaller than its own Hartog's number. This uses the equality for the full proof. C. Gilman. Kurt Gödel showed that GCH is a consequence of ZF plus V equals L, and is therefore consistent with ZFC, as GCH implies CH. Cohen's model in which CH fails is a model in which GCH fails, and thus GCH is not provable from ZFC. W.B. Easton used the method of forcing developed by Cohen to prove Easton's theorem, which shows it is consistent with ZFC for arbitrarily large cardinals to fail to satisfy much later. Foreman and Woodin proved that it is consistent that holds for every infinite cardinal. Later Woodin extended this by showing the consistency of for every. A recent result of Karmai Merimovich shows that, for each n1, it is consistent with ZFC that for each kappa, 2 kappa is the nth successor of kappa. On the other hand, Laszlo Partai proved that if gamma is an ordinal and for each infinite cardinal kappa, 2 kappa is the gamma th successor of kappa, then gamma is finite. For any infinite sets A and B, if there is an injection from A to B, then there is an injection from subsets of A to subsets of B. Thus, for any infinite cardinals A and B, if A and B are finite, the stronger inequality holds. GCH implies that this strict, stronger inequality holds for infinite cardinals as well as finite cardinals. Implications of GCH for cardinal exponentiation. Although the generalized continuum hypothesis refers directly only to cardinal exponentiation with 2 as the base, one can deduce from it the values of cardinal exponentiation in all cases. It implies, that is, page 147, exercise 76. When alpha beta plus 1, when beta plus 1 less than alpha, and where CF is the cofinality operation, and when beta plus 1 less than alpha n. In mathematics, the continuum hypothesis is a hypothesis about the possible sizes of infinite sets. It states, There is no set whose cardinality is strictly between that of the integers and the real numbers. The continuum hypothesis was advancing earlier work by Kurt Gödel in 1940. The name of the hypothesis comes from the term the continuum for the real numbers. It is abbreviated CH. Cardinality of infinite sets. Two sets are said to have the same cardinality by Georg Cantor in 1878, and establishing its truth or falsehood is the first of Hilbert's 23 problems presented in 1900. Tau's answer to this problem is independent of ZFC set theory, so that either the cardinal number if there exists a bijection between them. Intuitively, for two sets S and T to have the same cardinality means that it is possible to pair off elements of S with elements of T in such a fashion that every element of S is continuum hypothesis, or its negation can be added as an axiom to ZFC set theory, with the resulting theory being consistent if and only if ZFC is consistent. This independence was proved in 1963 by Paul Cohen,